Okay, so the question is, in our sugar and turkey example, would the weight of the plank make a difference? So let's think about it. If we had a plank that had no weight, and we had no sugar on it and no turkey on it, would it balance okay? If it had no weight.
You're not at that point.
At that point, with no weight, if it was an absolutely weightless plank. So what's going to make it turn? It's got no weight. What's going to make it turn? It won't turn. It's got no weight. Gravity's not going to act on it, is it? You can't get a weightless plank. But theoretically, if it had no weight, it's not going to turn. Yeah? Whereas if it has weight on it, it is going to turn, isn't it? And if we had a really fat plank, then it's going to turn a lot more. Okay? The idea of a plank is what we call, or the idea you're getting at here, is a universally, no, it's not universally, uniformly. I knew it started with U. It's lucky I didn't come up with umbrella or something that also starts with U. Okay, the word you're looking for is uniformly distributed load, which we refer to as a UDL. Okay, so in physics and engineering, you'll come across this term UDL an awful lot. Okay, that just means uniformly distributed load. Okay, so what we actually need to figure out is what is the mass of the plank and how is it distributed. So let's say that this plank that we're working with here, so this particular plank has a weight of, we'll make it a nice chunky plank, 20 newtons per metre. So about 2 kilograms for every metre of plank. So it's quite a solid plank. We used found a hunk of 4x2 or something out the back to balance this turkey on. Okay, so if the plank has a weight of 20 newtons per metre, then we've got to figure out how to take that into account. And like we've said, if we took the turkey and the sugar off, the whole thing would tip that way. So clearly the turkey is doing something to balance that. So we've now got a third force we have to worry about. We've got the plank weight we have to worry about. Okay. The idea with the UDL, and this is a really important idea, the UDL can be treated as a point load. Okay, that's what I mean by these things are point loads, just acting at a particular point. So a UDL can be treated as a point load acting at the centre of the UDL. Okay, so all you need to do is say, where's the middle of my UDL? So the middle of the plank in this case, and take that as the place where the single force acts. So this whole thing is 1.55 long. So half of 1.55 is 0.775 maybe. So we could put this load, okay, so this is the plank load, and it's going to act halfway along here. So along here, half of that, which I think is 0.775. Someone just check that out for me. Yep. Okay. So the plank load is 0.775 from that end. And the size of the plank load, well, it's 20 newtons for every metre. So if someone could do 20 times 1.55 for me. 50. No, I'm not buying that. It's got to be more than 20 because 20 is for 1 metre. So 1.55 times 20. It's got to be more than 20. 31. Yeah. So we have a 31 newtons acting down there as the plank load. And now we can try and figure out how big the turkey is to make that work. So when we didn't take the load into account, the plank, we had a 5 kilogram turkey. And now if we're going to take the plank into account, it's going to change. The turkey has to be bigger to help balance out this load as well. Okay, so let's do the same thing we did before. So which force do you want, which moment do you want to work out first? Let's do the one we did before. So we know what the sugar moment is. We did that before, didn't we? So the moment for the sugar was equal to 1.2 and 15. So 15 newtons acting at 1.2 meters, which was 18 Newton meters counterclockwise. Yep, so we know that. We know that the sugar is trying to turn it 18 Newton meters anti-clockwise. Let's do the plank. So the moment for the plank. Okay, so what's the moment for the plank? How am I going to calculate that? 31, definitely 31, times. Okay, so I've deliberately drawn the picture weirdly to confuse you. Times 0.6. Yeah, so it's in the middle of the plank. Where do I measure distances from? Whenever I'm measuring distance, I have to measure from the pivot. So the distance I want is that distance. So 1.2 minus 0.775, 0.425. Yeah? So trying to figure out how much the plank is affecting the turning moment. It's the weight of the plank times the distance from the center of the plank to the pivot. And that requires someone to push some buttons again. What are you about 13? 13 point, no, let's go for 2. Yep, and that is anti-clockwise as well. Yeah. So we can add those guys together because that's going to give us the total anti-clockwise. We add those two together, we get 31.2 Newton meters. Yep. So that's how much the turkey has got to balance out this time. Last time it only had to balance out the 18 Newton meters of the sugar. This time it's also got to be able to balance out the plank. Okay, so the moment of the turkey has to equal 31.2 Newton meters clockwise. And that equals force times distance. So the force equals 31.2 divided by the distance, which is 0.35 for the turkey, which comes out to be 89.1 units. Awesome. No, force, newtons. And change it into kilograms, so somewhere in the order of 9 kgs. So a slightly bigger turkey. Yep, so if we get it without taking the plank into account, we come up with a 5 kg turkey. And if we take the plank into account, in this case it turns into a 9 kg turkey. Yeah, yeah, we were smart enough, we took the plank into account. Yeah. Or we used a very small plank, I can't remember which way. See, this is a smart question from this man. We actually didn't. We used just a meter rule, so we effectively used a weightless plank, and it was fine. Didn't last. No, we balanced it like this. We balanced it until it balanced, because we didn't know what we didn't have any other weights to add on. We only had one bag of sugar. So we didn't have any other known weights to add on the other side. That would have worked, obviously, but we didn't have it.